Hello, my name is Mark Blanchot. I'm with ISEC Partners. I'm going to present harnessing GPUs for general purpose computing using better browser-based botnets. So what is this talk about and why should you listen to it? I'm going to discuss about harnessing GPU power within the browser in the intent to break cryptography. I want to show the interest of current and future possibilities of cross-platform botnets for cracking or general computation purposes. So I'm going to discuss about browser-based botnet to get permanent code execution in the browser, regardless of the platform, then how to leverage the GPU from within a browser for general purpose computing, and I will give some example about in this regard. So who am I? I'm a senior security consultant with ISEC Partners, which is part of NCC Group. I do application security in various areas. I have a past experience as a game developer. I worked with game engines and wrote a few basic 3D games, so that helped for this research. So we are going to talk about basic stuff here. Whether we are talking about cracking keys or hashes, we are talking about general purpose computing. And we need parallel computation because we are generating and comparing a lot of hashes. And we only care about the total computing power brought by the hardware. And a GPU, as you probably know, is by far the best in that regard. GPUs have a lot of cores and can execute massive amount of instruction per clock. And even though CPUs have higher frequency clock, the total computing power of a GPU is way higher than of a CPU. So there is another type of device that is used for computation purposes. That is the FPGA, which stands for Field Programmable Gate Array. It's a device that can be programmed after manufacturing, and they basically have programmable digital logic chips and can execute what you have written for them. So they're very specialized into what you want to crack, basically. Since they are dedicated to general purpose computing, they're usually built for with a lot of GPU cores and custom hardware that makes them super fast, and usually faster and cheaper than traditional computers with a bunch of graphic cards. So why not build a massive GPU farm for cracking purposes? For instance, on the right, you have FPGA devices connected to one computer through USB hubs. That does look pretty nice in the living room, but I'm trying to get something cheap here. And this is not really cheap. If you're not planning on making a business out of this, your GPU rig may end up more like this. So why? Well, people have been trying for a little while, but here's the main problem. GPUs evolve too fast. People are abandoning their rigs to get new ones, and this has been seen very well for Bitcoin mining. People are just buying rigs, selling them out, and it's too specialized. And they just come up with new options, new chips. It's always get faster, and if you really don't want to have a business with that, it's really not interesting. So yeah, GPU evolve way faster than CPUs, even more than twice faster in terms of gigaflops, which is what interests us here. So what other options do we have for cracking purposes? So EC2 instances. You could pay for the cloud with Amazon EC2 instances. That sounds great. You can get pretty powerful machines. You would be renting them. You wouldn't get the issue of dying rigs due to evolution if you are not constantly using them. You are basically paying for raw computing power. Now, are they really the best machines you could get for that price? Well, the NVIDIA Tesla is a very good card. They have extensive functionality, but a lot of things in them you don't really need to for what you are actually going to do with them. They have complex scientific operations, double precision floating point math, 3 to 6 gigs of RAM with ECC support. And it also seems NVIDIA downclocked the Tesla to be able to have them constantly running. Also, NVIDIA cards in general are not usually the best cards for the price. to do parallel computations and for cracking purposes, because they usually have fewer arithmetic and logic units than AMD cards. Even though they have higher shader clock, they have usually less total computing power. So I don't know if it sounds like the best bang for the buck, but they are very convenient if you want to crack things quickly, and they scale pretty well. But it's just relatively expensive, and I'll show a price comparison later on. So all of you should already know what is a botnet if you are here. But yeah, it's usually a large cluster of compromised computers, generally running Windows, that are used for different malicious purposes. They are usually used for distributed denial of service, spam, phishing, keylogging, sniffing traffic on the network they are on, click or view fraud on a few different services. And in regard to general purpose computing, which is what interests us here, it's not necessarily idle. Only a small percentage of PCs have a powerful graphic cards. Although a botnet called Zero Access used half of its node for mining Bitcoin, and Sophos estimated they could generate $2.7 million annually with that. The rest of the node were used for click fraud, where it generated 900,000 clicks per day. So it is true for now. Current botnets can only use a percentage of their node for computing, but it is likely going to change. New CPUs have on-chip graphic cards, on-chip graphics, and they are relatively decent right now. And they are going to be way better in the future. Intel Ivy Bridge, for instance, generally integrates an Intel HD 4000, which has a great support for recent technology. It even officially supports OpenGL ES3, which I'll detail later, which is great for what we are going to do, and consume very little, which could allow a botnet to be pretty discrete. Intel Haswell is supposed to be released this year, and it's going to be twice as fast GPU-wise as what we have in Ivy Bridge right now. And in 2015, details are still vague, but Intel Skylake could potentially incorporate an excellent on-chip graphic as well. So what does that mean? Well, it means computer in the future, even for simple desktop use, could be leveraged to harness computing power. So let's discuss about cross-platform. Only 5 years ago, attackers only had to target Windows for botnets. But they are not the main OS anymore. The market got bigger and security got better as well. A botnet spreading through unpatched floor is very expensive, as exploits are in the hundreds of thousands of dollars now. One solution would be to compromise systems that are not up to date and just use known exploits. But the problem is that they are likely older computers that don't have the better GPUs or even decent CPUs. And we are still looking for something cheap here. So what is a typical browser-based botnet? So it's basically a botnet limited to live in a browser, sometimes only the time of the web session. They are usually used for spam, click fraud, or DOS. The infection usually comes through a malicious or compromised website. They can technically be bigger than traditional botnets, but it's easier to target large number of hosts on popular websites. It is to note that they are also not really detected by any antiviruses. It usually runs in the browser. It mainly scans only what is stored on disk in general, so you really can't really detect any of those. So they basically have a lower infection duration, lower attack surface, but they make up for that with their size. Their limitation are that they have to stay in the browser space. They also are limited to only talk to domains they are allowed to talk to, and to the hardware resources available in the browser. So I will mainly focus on one purpose here, cracking. Well, now let's discuss how a better browser-based botnet could be built and what could be done with it. So here we can start correlating a little bit with rootkits and traditional software exploitation. The main difference is that we're going to focus on having code running in clients by using server-side flows, then use HTML5 functionalities and leverage different browser behaviors to stay alive. This is different in some regard to other browser-based botnets using client-side flows. One of the reasons I'll focus on server-side flows is that they are way cheaper because they're usually easier to find and people don't secure website as much as the traditional browser you use every day. So even without client-side flows, I'm going to show that an attacker can still do some interesting things within a browser. First of all, there are several ways toward code execution. The first one is through cross-site scripting. Well, even if XSS is kind of boring, it's still the most prevalent web vulnerability class. And it's nevertheless kind of the code execution of the web. And they are still there because companies don't usually fix them individually. Instead of just using the right framework or do proper testing, they are also relatively cheap because they can oftentimes be found with simple scanning tools. XSS also work on any browser, from mobile platform to any kind of browser that can execute scripts. So according to White Hat, XSS is the most prevalent website vulnerability, and it was in 55% of the websites they tested at some point. So they have a pretty massive amount of websites, and this was really the vulnerability found most often. So what is the problem with XSS? Or server-side flaws in general, that they are fixed relatively quickly. And a botnet would ideally require permanent code execution. So how to achieve that? Well, an attacker could do cache poisoning, for instance. The first way to do that would be through a local storage functionality used by the application. HTML5 introduced web storage functionality, which basically allows storing data indefinitely for a given domain. The storage is not deleted when the browser closes, and there is generally no expiration date. Other local storage features include Web/SQLDB, Firefox local storage, and it used to include Google Gears, but Google switched to using other HTML5 functionalities at some point. To use all of these ways of storing data, unified solutions have been created, such as Persist.js library, which is now trivial for developers to implement, and they can do that across platforms. So the interesting part here is that a script controlled by an attacker can easily modify the storage, and for this specific application on this domain, they can just poison the entire cache. And this could be a way toward code or permanent code execution. But for this to be possible, the site would need to retrieve the cache later on and use it in the DOM. So I tried to have a look at how sites usually use this local storage functionality. Some sites just cache JavaScript files as object literal in a JSON format. This file can easily be poisoned and would allow executing malicious code on the same domain. And this would be permanent, or would stay there for as long as the website decides to use the functionality or just clear the cache. It doesn't happen that often. Other applications store profile data in the local storage. For easy retrieval of user information or avoiding some load on the server, such as username or just basic profile info that are reflected on the page later on. So this can be poisoned as well, depending on how it's actually retrieved. So here you can see the garlic library, which is used for retrieving fields injected without any filters to the local storage. And it actually directly injected back to the page into the DOM. So it will be very easy to inject any code in there. Another interesting one, more used, gibberish AES, which encrypts what is stored in the database. Well, the problem with client-side crypto is that a script that has access to the DOM can easily retrieve this ultra-strong password here. This code comes from an example of their page, by the way. And they just encrypt poison data that would be reflected back on the page. So how much space do we get? And those local storage work on all platforms. Well, as you can see, it's supposed to work on most platforms. We get 5 megabytes per domain, which is way enough to injecting a massive payload in there. So let's talk about spreading to other domains now. Why would we want to do that? First of all, an attacker will not spend too much time trying to find an XSS on facebook.com, for instance. But other new or not that new use subdomains are definitely going to be weaker. Finding an XSS on a subdomain is the first step, but then attacking the main domain may need a few tricks depending on what the application does. Well, if the session token is a domain-wide cookie, that's easy. The script has already access to the main domain, so no work there. But the interesting part is that some browsers have some functionality with which it is basically possible to override cookies for other subdomains. Well, it may not work all the time, depending on the browser. And Michael Deluski listed the behaviors depending on the browser in this tab. And there are also a few tricks. So, for instance, Chrome. So as you can see here, actually you can't really see much, but it's pretty difficult to override cookies in Chrome. But some people at the last CCC, JCO and Rich showed that they could force a cookie to be used when putting a path value in this for the same cookie, and so that would allow them to actually override cookies for another subdomain. And so once able to overwrite a cookie, the attack surface dramatically increases, and a lot can be done. Triggering dumb XSS through cookies, for instance, as a site will likely trust them. Also, if the site uses anti-CSRF token in cookies and the body, it will be easy to overwrite it and perform requests that may potentially trigger XSS or other behavior that could be exploited. So I'm not going to spend forever on other techniques, as you probably got the concept by now. However, there is a very interesting attack vector here that I wanted to mention. So there were a bunch of issues a few years ago on proxy servers, where it was possible to poison their cache with malicious content using HTTP response splitting, which is the ability to inject characters CR and LF in order to split an answer into two HTTP responses. This attack would be devastating in that case specifically, as proxy server cache common files retrieved by applications, such as Google Analytics JS files or any files that are common to most applications. And the malicious code injected there would allow running a botnet across an entire company on most computers. So that's a bit out of scope, but I thought it was worth mentioning. One thing people don't realize with JavaScript is that it can access anything in the browser, as long as it runs in the same domain. So creating pop under windows, accessing and closing tabs is very easy to do. Having XSS on several domains would allow frame hopping in the browser, and code execution would be kept alive for a pretty long time. Iframes can be a great vector as well. Even though a lot of websites tend to be protected against being framed nowadays, even though this can be defeated if they use only JavaScript checks. But so, for instance, a compromised application could allow opening a tab containing an iframe on a website you're already logged on. And even though the attacker will not be able to do anything within the direct frame, they will be able to run code within the tab. And the user may not likely close the tab if their session is running on it. But this attacker would require knowing a bit more about the user, right? How would an attacker would know what the user does in the browser? An attacker would be able to know which website the user is logged on by simply retrieving an image that is only accessible when the user is logged. Same origin policy doesn't really apply when retrieving images. So if the user is not logged on the website, there will be an error returned. So code execution using different technologies such as Java, Flash, or browser plugins is also possible. And it's basically the same concept as JavaScript. So I'm not going to go too much into details. I wanted to mention ads specifically. So ad would be a more or less legitimate way to execute script within the user's browser. It would obviously run on another domain, generally iframed, so sites running the app would obviously not be able to access anything on the main site. but this would work great for harnessing GPUs. But it can be pretty expensive. That's one of the problems. I found out that MWR did some research on distributed cracking on the web using ads. They did some research and had a great way to distribute hashes. The problem is that ads are pretty expensive. The service they use asks for 50 cents each time a user displays an ad, which is really expensive if we really want to scale. So apart from this persistence problem, yeah, ads are going to be difficult to run across mobile devices as well, because they usually don't display any ads. And so yeah, that would be one of the problems with those. So this is very basic stuff here. You probably already know that, but before HTML5, a few items were able to bypass same origin policy for reading and writing, which were images and script tags. Well, read and write through images is very, very hackish. Error or success is a binary response, so you could technically communicate to a remote server just using images, because it would be very, very slow. JSON-P is the main mechanism you would use. It's basically wrapping callback in script tags that would allow retrieving data from another server based on what is sent to it. HTML5 made it way easier with cores and WebSockets. Cores allow to perform AJAX call to a domain authorizing it, and would allow communicate with an attacker-controlled domain very easily. WebSocket is a bit similar, except it uses TCP sockets, and so it basically do a first HTTP request and then use TCP sockets. Cross-origin communication with Flash is kind of similar. It can talk to any server authorizing it by putting a crossdomain.xml at the root of the attacker's domain. Oh, in regards to the botnet architecture, existing botnet architecture are pretty well documented already, but we can quickly go through them. So there are two main models. A centralized architecture with a single point of failure, where the command and control server would be able to control the zombies. And there is also this hybrid peer-to-peer architecture, where a command and control server would control zombies, having the ability to issue command to other zombies. This architecture can be rather complex and seems relatively efficient, but the problem is that it can be taken down if a zombie is controlled by researchers, because they would then be able to find out where the other nodes are. One interesting architecture uses Tor to hide and send commands, and it's probably more difficult to take down. This has been seen in more recent botnets, but it cannot easily be done with browser-based botnets. So we have to choose between the two first architectures. I think an architecture that could make sense here would be to have several different command and control servers that would each have a task related to cracking a specific hash or key, for instance, and each one of them would be related to a particular infection point. So if you can control one site, you can potentially have one botnet specific to this point, and then have other botnets spreading around for other sites to control. So afterward, a list of ranges of password of public dictionaries could be sent to zombies, and each node would be coordinated from there. And data that could not be computed by a dying node would be sent to another zombie. All right, so the most interesting part here. So what do we have to harness GPU in the browser right now? The main technology is OpenGL ES 2.0, and it is basically used by WebGL, Flash, and NACL. So WebGL is basically JavaScript with shaders. It allows using the GPU without any plugin in the browser, and it is integrated by default by most browsers by now, well, apart from IE, even though there is a plugin for that. NACL, standing for Google Native Client, allows running native code in a sandbox within the browser, allowing to run code pretty fast, basically. OpenGL ES 2.0 is pretty powerful for graphics, but not really made for general purpose computing. So you can see a demo of Bastion here, a game just using OpenGL ES within NACL, some WebGL demo. So it's, if you have seen it running, it's pretty fast and it works pretty well right now. So OpenGL ES, the ES standing for Embedded Systems, it's basically a stripped-down version of OpenGL. and it has some additions, making it suitable for mobile OSs. To talk to the GPU, the OpenGL shading language is used, which is GLSL, and is a high-level shading language allowing to run on most platforms. So shaders are basically small programs that run on the GPU and can run in parallel. It is to note that Windows does not directly run OpenGL ES, but uses a wrapper around DirectX with Angle. It basically translates OpenGL ES API to DirectX 9 API calls. So what about general purpose computing using OpenGL? As I said, OpenGL ES is not really supposed to do general computation, but this can be more or less hacked. So basically, a stream of data flow through vertex and fragment shaders. A fragment shaders is a program that allows performing operations on the color and depth of a vertex. By implementing a hash function in a fragment shader, you can compute hashes directly with the GPU and retrieve the result by reading pixels in a frame buffer. So even if that is technically possible, there are huge limitations right now in the OpenGL shading language. I'm going to show why. First of all, it is based on an old version of GLSL and has a lot of limitations like 16-bit integers, and implementing hash function within 32 bits without 32 bits integers is very slow. So one solution is to use vectors containing two floats, but it's kind of slow, obviously. But the main issue, speed-wise, is the lack of bitwise operations, which are reserved for future use in the spec. So how do you still make it work? Well, you just need to re-implement bitwise operations, such as XOR, for instance, here. So it is very hackish, but it does work, even though it's very, very slow right now. So OpenGL ES2 is very limited, and it is going to be way better in OpenGL ES3 that I'm going to show. So first of all of the previous limitations are going to be resolved. It will support 32-bit integers as well as bitwise operations, and will allow doing the hack I mentioned to compute hashes with WebGL. So this is pretty good for this botnet, even though I don't really know if it's going to be when it's going to be implemented. Probably soon, but we don't really have any dates. The standard came out in August last year, and it is already officially supported in Intel Ivy Bridge. So it may come out anytime soon. I don't really know. But it will come out. This is the next version of OpenGL ES, so it will definitely come out. So what about cross-platform with OpenGL ES? Well, it works on a lot of platforms, as you can see here, including mobile, game console, and even smart TV. What about WebGL now? So what interests here is to use OpenGL in a web browser. And there is less platforms than platform using OpenGL ES. On Android, it is still beta, but it can be enabled with a simple flag, so they are actually planning on implementing it. And it does work with the flag. On iOS, it is supported, but not enabled right now. It is also implemented on various platforms by default, and maybe even on the PS3 one day. Basically, as long as OpenGL ES is on the platform, it shouldn't be too far-fetched to think that WebGL or another technology will integrate with the browser. So let's talk about OpenCL now. So this is basically the technology used by applications to crack hashes, such as Hashcat, for instance. It heavily focuses on parallel computation and on giving application access to non-graphical computing power in order to perform general-purpose computations. AMD and NVIDIA drivers both support it. Now, same as WebGL with OpenGL ES, there is a JavaScript binding for OpenCL that works in browser, and it's called WebCL. Unfortunately, it requires a browser plugin for now, but plugins are already available for Chrome and Firefox. And Firefox is actually already currently implementing WebCL into the browser. we get great results with it. It is basically the fastest browser-based tech for parallel computations. It is only the beginning of implementation. It would be way faster if it weren't running in a plugin. So these technologies are great and would allow running pretty powerful botnets on the web once they are implemented. There are a few challenges. Now, having such a botnet would obviously lead to a few issues to consider. Cracking would have to be done when GPU is idle, but this would be done at night or when the device is charging, for instance. There is also this bottleneck in the node management and distribution with like dying node and all of those things to handle can be a bit tricky, but doable. In any case, it could still be a potentially viable botnet in the future. So we will see what it means and what can be done with it. So there is a lot of unknown regarding the computing power this botnet could get in the future. First of all, how many clients could be compromised and for how long? Also, one tough question is, what is the average GPU now and what will it be in the future? So, I mean, in terms of how we can list them, at least we can know what is the average gamer GPU because people like to just show the GPUs they use. So you can find some stats on Steam, which is a platform with millions of players, so you have massive amount of data there. And interestingly enough, the most used is an Intel on-chip GPU, which is the Intel HD 3000. But for the other computers out there, it's a bit more difficult to estimate. But at least the recent one have on-chip graphics now. So today, a decent GPU can get about 20 to 50 mega hashes per second with WebCL and MD5 computations. In the future, let's say an average GPU could, with on-chip graphics, could get about 10 mega hash per second. And do not forget that WebCL could be way faster once implemented to browsers. Also, in regards to the number of clients I will consider, I think we could take larger numbers for a classic botnet, seeing the number of users on popular websites. And yeah, each user has a number of devices as well, so it has to be taken into consideration. So here are some graphs. As you can see, computing time difference at this scale between the weak MD5 and SHA-256 is not that big. It's only one character difference in terms of time it would take to actually crack it. So this is for most characters, special characters, numbers, and most characters people use when they choose passwords. Cracking FIPS compliant keys is also possible to some extent here. So I will detail that later, but this is a password-based key derivation function with using SHA-256 and 1000 round. So let's put some context on these numbers. Cracking MD5 with 100,000 clients would get 1,000 gigahash per second, and on a larger scale, 1 million clients would get 10,000 gigahash per second. To put that in comparison, one of the fastest FPGA barely reaches the hundreds of gigahash per second. Even though there is an exception, a product meaning Bitcoin is promising to reach 1000 gigahash per second when it will be released, but this FPGA is worth like 30K and only specializes in Bitcoin. So it's a very specific FPGA with very specific chips as well. It's not even released yet. Let's take another example. Going through all 10 characters with, for a password with MD5 would take a day with 4 million clients. And it would cost $4,000 with Amazon. Assuming we get around 2,000 mega hashes per second with Amazon, which is what you usually get with Tesla cards. So it is to know that if we follow the same GPU evolution over the next 5 years, it may only take a few hours to crack the same password. And even though it is true that Amazon would scale as well with better GPUs in 5 years, it is something to take into consideration. So what could an attacker do with this computing power? Well, I think it's important to mention that hash functions used for password can all be cracked to some extent, depending on the amount of entropy of the password. And as we've seen in the previous graph, on a large scale, using only MD5 or SHA-256 doesn't make that much of a difference, as it is not really made to be computation intensive and can then be cracked. Round of hashes are better to store passwords, even though they are still crackable, as computations can be parallelized. So again, entropy is key here. bcrypt or scrypt are kind of the solution for storing password right now, as they are methods that cannot be parallelized easily, as they take a lot of RAM to compute. So companies should use it more, and but they should be aware that they could also be vulnerable to DOS when they actually compute the password. So they need to make sure to implement to throttle requests. Another use here is Bitcoin. Well, this is probably what botnets tend to do right now. This could obviously allow an attacker to make a decent amount of money, and I guess that would be the main thing we will see in the future when people start implementing that kind of botnet, if they start doing it. So what about keys? Well, as we saw in the graph, password-based key derivation with 1,000 iteration is not going to prevent from brute force. Again, it depends on the entropy, but deriving a password using that algorithm is not ideal if the password doesn't have high entropy. So obviously, weak keys, which is usually everything below 128 bits, and a target you could think no one that use that kind of key anymore. So yeah, I've seen several times people using 40 to 56-bit keys, and it's really easy brute forceable. And you can see that in bad SSL configuration, for instance, or in products using just weak keys, as they don't realize it can be easily brute forced. So now in terms of asymmetric algorithms, whether RSA or DKIM, so DKIM is something that could be cracked to spoof emails. That's something you include with emails for verifying a domain. It has been cracked at some point recently. They used very low entropy key, but as long as it's below 1024 bits, that should be fine in that regard. So in regards to factoring 1024-bit keys, the feasibility with very expensive and custom hardware has been mentioned in a paper by Aaron Trommer, but it won't be feasible anytime soon with botnets. You really need very specific hardware. It hasn't really been done in any case, so it's really something to, think about it, but not really consider for that kind of application. So I kind of mentioned these already. NTLM is pretty weak. It's usually even twice faster to crack it than MD5 due to the use of the LM algorithm. It has been shown pretty recently with a few password cracking FPGAs for that specific algorithm. So it is really, really weak. On the phone. So I think this example speaks by itself. Could you, if you tried, type this password with your phone each time you need to unlock it or log into a product? Well, probably not. And that's the problem with phones right now. Any data encrypted on them rely on a key derived from a weak password. Yeah, a few examples of types of products that could be tested. I wrote a paper about use of weak keys that could be brute force in secure containers at some point, and should be online on the ISEC Partners website soon. And I think there are a lot of applications that use very weak key or keys that could be easily brute forceable. So I think it would be good to test those products for making sure they don't make the wrong assumption regarding what you could do with those keys. So even though this browser-based botnet cannot be used at a large scale yet, the technology may come sooner than you think. As OpenGL ES 3.0 may come soon, and when WebGL is already being implemented in Firefox, for instance. Regarding the botnet part itself, HTML5 added so many things that it is now possible to have a pretty persistent botnet running. And I'm not saying HTML5 is bad, because it added a lot of things that are that made it way easier for developers, and it added a lot of great functionalities. But they should be aware of the new risks and know how to properly secure their applications. Using browser-based botnets can be pretty efficient and cheap for cracking. This increases the scale, and companies need to be aware of it. And they have to stop thinking that only government entities can perform decent brute force when they design their crypto. Attackers have other means. All right. Is there any questions? All right. Thank you very much for coming.